URL, which is a link to our website, the knowledge base, and that will hold all the information about the format. Have the version of the format if that's global, and you can also have a version for each of the signatures. And you have the priority, but we'll talk about that a bit later. And you have the author of the packer. So that's the basic information that's been held in the database at all times. Now you have a default database with the program itself, which is loaded each time you start the TitanMist, or you can create your own database and just use that database as your reference point. Now the identification part is first part of the TitanMist project, and it is very important because since we are building a specific AMP packer for a specific file format, we need to know which format it is and know which version it is. So these signatures are laid out in a database, and they can be both simple and complex. They are grouped into entries, so as I said, you can have multiple signatures for a single file format because there are different versions and packers evolve over time. And detection is either global by the entry, so you have one version for the entry, and you can have specific detection for the signature as well. And the entries are linked to the AMP packers, which are called once you tell the TitanMist to unpack the file you're interested in, and they are both linked to the online knowledge base. So when we started coding this project, we asked ourselves, what are the reference points from which we have to start our pattern matching? So we have a couple of these. So we can start the pattern matching from the start of the file, and that can be useful in many situations. We're going to talk about that a bit later as well. And we have the standard identification, which starts from the entry point of the file, which is in the stub. And we also added something that could be useful in the future, and that's pattern matching from the overlay. So those are the basic pattern matching options you have for each of the signatures. So the identification can start from the entry point, and these are the default settings listed. So for the entry point, the default is match a pattern. For the overlay, it's a match a pattern as well. For the beginning of the file, it's also matching. But you also have a switch that enables you to scan the entire file for the selected pattern. Now, since these are the default values, they can be overwritten. So each and every one of these patterns can be switched to seek, which means just search for the pattern from that reference point. Now the simple patterns, if you use PID before, it has the user database which contains lots of these signatures, and the most basic signature type is the one we refer to as the simple one, and it enables you to create a simple pattern that identifies the format. So we can have wildcards which match any byte in the sequence, or you can have bit masking that either matches the high or the low bit. So for example, if you look at the screen, that's the simple UPX pattern that has wildcards for the both byte and the bit masking options. Now we looked at this and said, okay, this is fine, but we have to improve this if we're going to have more complex patterns that can identify formats better. So to improve this, we first identified the problems. And the problem number one we identified, and if you look at the code, that's basically just a UPX sample, and that's the entry point of the UPX stub. So the highlighted part shows a random number of NOP bytes, which is just an NOP sled, and for different versions there are different numbers of these bytes. So in order not to have too many signatures for just UPX, we added a wildcard to our pattern matching, which looks like this. So our complex pattern matching would look like star, then our pattern, and then in the parentheses, you will have the byte which repeats indefinite amount of time. So for the previous sample, that would match NOP or byte value 90 for as long as there are NOPs, and after that it will just continue pattern matching. So this solves a couple of problems. This solves a problem where we have bytes that repeat each other, but we don't know the exact number of repetitions, and this solves the problem of having too long of signatures in our database. So that's the first problem we tried to solve, and that's how you apply it to the previous sample. So the problem number two we saw. The problem number two identifies to the random bytes that can be used as well. So if you look at the highlighted part, that's a jump. And throughout the versions of UPX, that jump can have certain values. So it can increase or decrease in jump in jump length. So in order to have a simple signature that's not just going to be a bit masking for the value of the jump, we added ranges. So if you look at the signature now, there's another piece of it which is highlighted, and it indicates the range in which that particular byte is. So if the range is in between 00 and 7F, that byte is always going to be, that jump is always going to be in the positive direction. So you can indicate that as well. And you can make these rules as you like. Now, this solves a bit more problems, not just jumps. It solves the problem of register permutation as well, because you can select a range in which the registers are present inside the instruction. So you can indicate that as the part of the pattern as well. So another problem that we notice while working on unpackers is the problem of that certain code can be there just in certain cases. So for this particular example, and this is UPX as well, and this is a dynamic link library. So the first two instructions that are highlighted are only there if the file is a dynamic link library. So the rest of the signature would apply, which we just written, would apply to this as well if there weren't for these two instructions in the front. So what we did is we added an optional part of the pattern. So the highlighted part says that only if the entire piece of the pattern is present, that piece of the pattern is valid. So if the piece of the pattern is present, the pattern matching will continue from the byte 60. And if it's not present, the optional part will just be skipped. And this solves all sorts of problems as well. This solves the problem of optional instructions, as we just saw at the entry point, but that can be in either place in the file. And this solves the multiple signatures problem, because now we don't have to have two signatures, one for the DLL and one for the executable for the UPX. Now another problem we saw is, this example is ME WPacker, and it has a jump at the entry point which leads to the specific location inside the portable executable header, and at the statical address in the header you have the code which is an entire stub for that particular packer. So what we did is we added the following complex pattern which enables you to jump skip. So if we set the pattern matching from the beginning of the file and we match it to the first 2 bytes, which is just an MZ for the header, and we say, okay, jump the certain number of bytes, that would be 152 in the MEW case, so that's hexadecimal, and then we can just continue our pattern matching. So this will compact our signature. We don't have to have 152 hexadecimal decimal wildcards, because there's really no need for this. And this jumping can go either way, so we can jump in either positive or the negative direction, which makes our signatures non-linear in comparison to PID, because PID signatures are linear and they have to have one byte after another, because now we can jump backwards. Those signatures cannot be, they can be non-linear as well. So we can match a certain point of the pattern and then jump back to confirm it or do whatever. So, of course, this also solves many problems. It solves the problem of increasing the size of the byte pattern, and it solves the problem of patterns having to be linear. Now the next problem is also very interesting, and this is PE compact. And as you see at the entry point of PE compact, we have the first layer, and the first layer only does the initialization of the structured exception handler, and you have the string that identifies that as the PE compact following this. Now for the PID, classical PID signature, which just matches the entry point, that signature would be way too short. So that can be spoofed and easily spoofed. So what we said is, wouldn't it be nice if we could just follow the value of move EAX and just continue our pattern matching there, because that's the second level of the packer, and everything we need to have this better kind of pattern matching is right there. So why not do that? This is a combination of the previous feature and this one. So this pattern matching enables identification of PE compact in the first layer. So if you see the bytes until the first highlighted part, that's the first layer. And then we jump back. As I said, we can jump back as well. So we jump back to the beginning of the pattern and we match B8 again and say, okay, follow that D word. And we will end up in the second layer of the pattern of the packer and just continue our pattern matching there. Now this is the way we can have complex patterns which enables us to have better quality pattern matching and be sure that the pattern we have matched is really that signature, because, as I said, if we only match the first part, this would be way too short and way too easily spoofed. So this also solves the problem of patterns not being linear, because now you can just follow the words anywhere you want, and you can just continue anywhere you want. And the next problem is related to the previous one, and we said, okay, if we can follow the words, why not follow calls as well? So because this is a nonlinear signature now, we can follow calls and continue our pattern matching inside them. So this is an example of shrink warp, and it has a couple of calls that follow into each other, and we said, why not have a pattern that can identify this? So this is how it looks like. First byte is, of course, the identification for the call, that's E8. And the following that is our pattern that indicates that that E8 is actually a call, and it's 5 bytes in length. And the plus means that it's always in the plus direction, so it's jumping down in the code. That's also one of the parameters we check for. So if we have a E8 byte, which is followed by 4 bytes, of course, because that's a call, and it's always if it's in the plus direction, we can just follow that and continue pattern matching from the first byte inside a call. And as you can see, there are some other calls inside the pattern as well that we just follow. So this also solves problems to the byte patterns not being linear, and the problems of having way too big byte patterns as well. So if we were just to have a byte pattern that takes into account all the bytes in between this and the call where it starts, we would have way too big of a pattern. Now the last problem we saw, and this is the problem of sliding pieces of code. Now this is a code which can be located anywhere inside the code, and this is ASPAC, and that particular piece of code does import reconstruction, so that's a call to get proc address somewhere in there. Yeah, call. Okay, so what we said, okay, there's different versions of ASPAC, and this is never at the static location. So if we have a static signature which is long enough to identify ASPAC, why not have another signature inside it which validates that our unpacker will actually work? So what we did is we added searches to our patterns. So inside a specific range, and you see the highlighted part, so inside the range which goes in the plus direction behind the matched pattern says if it's inside the range of 300 hexadecimal, and if there's this pattern, then you just continue pattern matching from there, from the point where's the last byte of your match. So if you have a couple of these searches, we can just match if they're all, if we have all the patterns we need to actually unpack this file. So now the identification and unpacking are related, because if this is a single layer packer, which ASPAC is, you can just match those patterns you need for the unpacking to work inside the identification process itself. So you know that your unpacker will work before you actually start the unpacking process. And that's now the part of the identification. So that solves problems as well. That solves the problems of byte pattern not matching, because, as I said, this can be at random positions in the file. And it enables us to embed unpacking patterns inside identification. So last but not least, we recognize the fact that there are some packers out there that can sign the file falsely. So we have this packer, which is called MSRLH, and it has an option of inserting fake signatures for those basic formats such as UPX and FSG. So we said, why not check for these byte